Hi there, Mr. Holcomb here with another lesson in pre-algebra. This is Unit 6, Lesson 4, Session 1, Understanding Congruence. Okay, so for starters, be curious, what questions can you ask? Well, if we look at a diagram like this or a photo like this, we could probably say, well, could I duplicate this peak for starters? And if I can I move it up to the another one? And is it the same like so? And if I moved it over here, is that the same pitch? Okay. So that's what a roof is called. It's called a pitch. Rise over run. It's a slope, a pitch. Okay, so that is one question, and there will probably be others, but we'll leave that to the class. So here's the first thing, a new patio. A landscape architect has designed a new patio for a client. The client wants to verify that the first table is the same size and shape as the second table. How can the architect show that the two tables are the same size and shape? Well, the architect, I guess, could, in his drawing, have a layer that has the table on it and be able to move that. So let's first start with a 90-degree rotation counterclockwise, and then move it left, and then move it down. And then when we place it there, we see that it does have the same size and shape. So it has been either a rotation followed by translation, or maybe it was just a rotation from a point somewhere over here. So it rotated around and ended up there. So 90 degrees clockwise rotation. Okay. Or we could have reflected it across and then rotated it and then shifted down. There's many ways we could do it, but just moving that over here and rotating it 90 degrees puts it right on top of the table, and they are the same size and shape. So how can transformations used to compare size and shape? Well, just like we did, you can transform a shape onto another shape and verify that it has the same length of sides and the same angle measures, which would give us the same size and shape. Okay. Okay, so a better wording would be, since some transformations are rigid motions, they preserve size and shape of a figure. So we could use rigid motions to determine if the first table is the same size and shape of the second table. And those rigid motions are translations, rotations, and reflections. Okay, and I just answered that, didn't I? Which transformations could we use to compare the size and shape of the two tables? Well, like I just said, rotations, translations, and reflections. Okay, so how does the orientation of the first table need to change to match the orientation of the second table? Okay, well, they're going the other direction. They didn't say which table was which, but if you move this table over to here, this would be the first, this would be the second. If you move this table from here to here, that would be the first, and this would be the second. So it doesn't really matter. So what they did in this step here was shift it right and then shifted it up. Okay. And on this one, we'd have to shift it right and shift it up and then rotate it 90. Or maybe we could just rotate it around a center point like here. So let me draw let's see if I can do this with this program. So if I drew a table like so, and if I put a center, oh, I don't know where it would be. I want this to end up here. So somewhere over here, let's put a dot right there. And then I'm going to group those two pieces, this and this. And then I'll group them. And if I rotate them, now look where the dot is. It's right on the corner of this white rectangle. So if I rotate this 90 degrees, it's obviously moved. But then if I move this up to here, okay, that's pretty close right there, but we're off a bit. So my center of rotation was up a little bit further, maybe here. So let's try that. Okay, so I just want to make sure that this is clear. So if I put a dot, how about, oh, right about here. Okay, and then I click this and group them, and then rotate it 90 and put that dot back here. Okay, it's still off a bit. It's got to be up higher. But anyway, if we knew where the center of rotation is, this is a 90-degree counterclockwise rotation, and the table would land right on it. Say, rotating it around, it would kind of come down, rotating, and end up landing here on a 90-degree rotation. Okay, I just have to find the center of rotation, and that's a little difficult without drawing some other lines, and we're not in that. We haven't gotten there yet, so we'll work on that. A new patio. A rotation of 90 degrees clockwise would turn the table from horizontal to vertical. Okay, so that's what they're showing in this first diagram with this red arrow. Two figures are congruent if one can be mapped to the other with a sequence of transformations. So a sequence of transformations. So are the two tables congruent? I believe so. Okay. So a landscape architect, okay, we've already read this. How can the architect show the two tables are the same size and shape? Here's the answer. The architect can use a series of transformations to show that the two tables are in fact congruent. Two figures are congruent if one can be mapped to the other with a sequence of transformations. So let's explore more. Could the architect have first rotated, then translated the first table to map it to the second table? And the answer is definitely a yes, of course. Yes. Okay. The order of transformations does not matter as long as we end up at the new location. Okay, so we could reflect. Then rotate. And then reflect again. Okay, so if I drew a line here and reflected this over to here, then rotated it 90 degrees and then reflected it across a line here, then those would work. We could do a single rotation, like I said, where the center of rotation is probably up here more, and rotate this whole table around there. Okay, there's many ways we could do it, and there's many orders of which we could do it. Okay, so that is the end of session 1. Hello there, Mr. Holcomb here with another session in pre-algebra. This one is Unit 6, Lesson 4, Session 2, Understanding Congruence. So be curious, is it always true? Valentina states that the area of figure A can be increased if a sequence of transformations is performed. So in other words, what she is thinking is she could shift this over to the right, rotate it, reflect it, all that, and change the area. And it says, is it always true? No. Okay, the area A cannot be increased by a sequence of transformations unless it's a transformation we haven't done yet, and I haven't gotten there yet. That's next lesson. So I would say no. Transformations or translations, rotations, and reflections are rigid motions that maintain or preserve size and shape. Okay, so if it maintains size, then area cannot be increased. Okay. So is quadrilateral EFGH congruent to quadrilateral IJKL? Well, what you can do is EF is a length of 1. IJ is a length of 1. This is 1, 2, 3. This is 3. This is 3. This is 2. This is 3. So right there is a problem. There is not congruent. So what sides and angles appear to correspond to each other on the quadrilaterals? Well, EF and IJ, FG, and you got to go in the same order, top to bottom, J to K, GH, and KL, and finally HE and LI. Oops, not LE, LI. And this one here, that group, HG and KL, are not congruent. One's only 2 long and one's 3. Okay? How can you transform quadrilateral EFGH so that it has the same orientation as quadrilateral IJKL? Same orientation. Okay. How can we transform that? Well, this is 3 long and this is only 2. So, but if we're going to have the same orientation, the size is still not going to be the same. We would have to reflect across the y-axis and then translate up. Okay. So here's the first step. We would have to reflect across the y-axis to get this over to here. And then the next thing we'd have to do is translate up 4 units to possibly map them to IJKL. So this is an image. So it's primes, E prime, F prime, G prime, H prime, where the pre-image was over here. So we reflected it across, and then when we move it up, we will see that H will end up here. So this would be H prime, H double prime, which would become L. And it missed by 1. Okay. So after we reflect and translate, we see that they are not the same shape or size. So after reflecting and translating quadrilateral EFGH, the image still does not match quadrilateral IJKL, side KL, and G prime, H prime. The bottom ones are not the same number of units, and side IL and side EH, therefore, would not have the same slope or the same length. Okay? So are the 2 figures congruent? And how do you know? And the answer is no. We already stated GH equals 3 units, where KL equals 2 units. And when we do 2 transformations, those 2 should correspond. And they, to be congruent, they have to be the same length. So the answer is no. Okay, so no, the 2 figures are not congruent because KL and side G prime H prime do not map onto each other, and side IL and E prime H prime do not map onto each other. So transforming figures, 2 figures are congruent if there is a sequence of rigid motion transformations that can be used to generate one figure from the other. Quadrilateral does not map, EFGH does not map onto quadrilateral IJKL. Sides KL and GH and sides IL and EH are not the same length. This is very repetitive. Therefore, the 2 quadrilaterals are not congruent. Okay, and so how can generalizing be helpful in solving the problem? Okay, well, if we do the transformations and move them, we can see that they will not land in the proper locations. Okay, so A says, how can you determine whether quadrilateral A is congruent to quadrilateral B? Well, we could rotate it. So if we're going to move one, we could move A to B. We could reflect, well, let's see, how could we do this? We could rotate it 90 degrees clockwise. So in doing so, let's do that. So this point right here is -1, 1. If I rotate that 90 degrees, it's going to end up at 1, 1. If I have the point negative 1, 2, 3, 4, comma 1, that's going to become 1, comma positive 1, 2, 3, 4, which is here. So this bottom piece here is now, oops, let me just do this, is now right there. Okay, and if we continue, point negative 1, 1, 2, 3, rotated become 1, 2, 3, positive 1. That's right here. So that's this point. Now would be here. And then when I draw a line, segment from here to here, there it is. And then get my pen back. And now I'm going to plot negative 1, 2, 3. 1, 2, 3 will become 3, positive 3 with a 90-degree clockwise rotation rule. And now we know where all 4 vertices are. And I can complete this like so. Okay. Next thing I'm going to do is I'm going to create one piece. I'm going to now make this all one piece. And then if I shift it down 1, 2, 3, 4, it should land right on top, which it does. Okay. So how can you determine? Rotate A, okay, quadrilateral A. Okay, I should write the word, but I'll just write this for now. Rotate quadrilateral A 90 degrees clockwise, followed by a translation down 4 units. What sequence of transformations can be used? Well, there it is. How do you determine? All right, well, I guess this is the answer for down here. So I guess I'll move this. Rotate A 90 degrees clockwise, followed by a translation down 4 units. How can we determine whether the quadrilateral is the same? Well, we could have done this first and see that the size is the same. Or what we could also do is say this side is length 3, this side's length 3, this side's length 2, this side is length 2, this side is length 2, this side is length 2, and this is going diagonally across 2 squares, and so is this. Okay, but those are not length 2. We'd have to do the Pythagorean theorem, which we haven't done yet, to get the length of that diagonal side. Okay, so we can verify that the 4 sides are congruent. Okay, translations, reflections, and rotations all preserve the size and shape of figures, and we classify all these as rigid motion transformations. 2 figures are congruent if there is a sequence of rigid motion transformations that maps one figure onto the other. So if we reflect, this is a reflection across the y-axis, maps triangle ABC to triangle GFE. So A goes to G, so that's, and the letters have to be in the right order. A goes to G, B goes to F, C goes to E. Okay? So that is a reflection across the y-axis. All right? So let's apply this information. Sheet metal cutter. Sheet metal is cut as shown for parts for a machine. The design is programmed so that the machine automatically cuts pieces over the entire given sheet of metal. Question: what transformations does the designer use to program the sheet metal cutter? Okay. So what he's doing is going to make multiple copies of this. So what I would suggest would be to copy this. Let's not worry about the circle and all those dots in the middle. And we're going to make a rectangle the same size, like so. And then I'm going to copy it. And I'm going to translate this over like so. And just to save material, you could have the cut side right next to the other one. So when it cuts this, it's the left side of the image and the right side of the pre-image. And that is a translation of 1, 2, 3, or 1, 2, 2. So I went from 3 to 5, and I went from 1 to 3. So if I duplicated this repeatedly, oops, if I move this up like so, okay, and just made multiple copies and just kept translating to the right too, and then move this over like this. Okay, I can't do it again. I'm going to run out, but then I could translate up 1, 2, 3. So if I took this and moved it up 3 units, 1, 2, 3, we'd be here, and then do it again. So if I move this up from here, 1, 2, 3, okay, we're right on the edge. We might not be able to get that piece off. All right. So anyway, if we were to do this, if they move this one over a little bit and down, we'd be able to get 1, 2, 3, 4, 5, 10, 15 of these shapes cut out of one piece of sheet metal. Okay. So what transformations could he use? He could do a reflection, or he could do a translation, or he could do a rotation, but I don't see where that's as beneficial without wasting material. Okay, so translations and reflections would work. Translate right or translate up and right would get us all these rectangles of the same size and shape. Okay, so that brings us to the end of session 2.